Uh, maybe I do. Sorry. I'll see my screen.
Yep.
Is that okay? So should I start? Is the organizer okay? I start. Can you tell me whether I can?
We can start.
Okay. 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 It's like play. So I opened the YouTube video, so I heard my sound twice. Anyway, so I start. So thanks everyone for coming. Is someone open the speaker? Yeah. Sorry. Okay. Wait. Okay. I realized I opened the YouTube and it played the sound. So it's okay. Okay. Hello everyone. Thank you for joining today's webinar. I'm Dicky Wang from ETH Zurich. I will be your host for today's AsiaGraph Web Seminar Section 23. So we are very honored to invite two great speakers today. Professor Young J. Kim from Iowa Women's University from Korea, and Dr. Yijiang Huang from ETH Zurich. Today's webinar focuses on robotics and how it's integrated into the graphic research. So for our first speaker, Professor Young is a full professor of computer science and engineering at Iowa Women's University. His research interests include interactive graphics, in computer graphics, computer games, robotics, AI, haptics, and geometrical modeling. Has published more than 100 papers and received award from ACM Solid Modeling in 2003, International CAD in 2008, and Geometry Modeling and Processing in 2006. He also received Outstanding Research Case Awards from Korea National Research Foundation and the Korean Ministry of Knowledge and Economics in 2008 and 2011. He's currently the president of the Korean Computer Graphics Society and the vice president of the AsiaGraphics and executive committee member of EuroGraphics. He serves on the editorial board of Journal of Computer Animation and the Virtual World, the International Journal of Computational Geometry and Applications, and advanced in robotics research. Since 2022, he has served as a review board member of National Research Foundation in Korea. The title for his talk today is Artistic Robotic Drawing on Large Non-Planar Canvas. So Professor Yang, the floor is yours. I stop sharing and you can share your screen.
So can you see my screen?
Yes, very clear.
Okay, right. So thanks for the long introduction. I appreciate it, Dr. Wang. So my name is Young Kim, and I'm a professor at the Ewha University in Korea. So it is a great pleasure and honor to be invited to this webinar and to give a talk to people, even though it's online. So as I was introduced, this talk is about kind of robotics problem, but more in the context of the graphics. So we'll find this talk somewhat intriguing, even though you are probably most of you might be in the graphics area. So most of the contents of this talk is actually taken out from my recent PhD graduate, Dawn. Now she's at UMD, and also my colleague at the Gettysburg College, Professor Ivailo Ilkin. So the motivation of this work was something like this. So you have seen this kind of large wall drawing in different places, like in France, or these are the large wall paintings in Busan in Korea. And probably the culmination of this kind of larger wall drawing is this gallery of Sistine Chapel in Vatican City, which was done by Michelangelo in the early 16th centuries. And as you can imagine, if you ask human to draw this kind of complicated drawing on a really large wall, or to make it even more worse, if you have to draw on a bumpy, non-flat covered larger wall, it'll be really difficult and time-consuming. For example, in this case, Sistine Chapel, Michelangelo took almost 4 years to complete this. So the research challenge for us was how can you use the robot to create this kind of artistic drawing on really large, non-flat canvas. So this was our research goal. So we were interested in creating robotic system that is capable of drawing pen art on a large non-planar canvas using the existing high degree of freedom manipulators. So here I'm going to show you kind of about 3 minutes video to summarize our research. Let's watch this video first for about 3 minutes. So I will stop here and then move on to the technical aspect of this work. So to realize this kind of robotic drawing for large non-flat surfaces, we have to address these kind of typical robotic challenges, including sensing and planning and control. For the sensing problem, first of all, we need to figure out how the target canvas geometry looks like. So we need to somehow reconstruct the target canvas geometry so that the robot arm can draw drawings on the canvas. As to the planning problem, first of all, we need to get or generate the drawing path or sequences for robot so that the robot arm can follow such a path to create the drawings. So this is some kind of planning problem. You need to find the proper way of drawing poses. And then if you are given really large canvas, even though robot arm is relatively long, it cannot reach everywhere on the canvas. So it is kind of mandatory to have a mobile robot attached to the drawing manipulator so that the manipulator can move around to draw really large canvas. Then this is a typical planning problem where you have to locate the configuration or pose of the mobile manipulator so that it can completely cover the drawing canvas so that it can draw the entire drawing. And finally, the control problem that we are particularly trying to address here is that the sensing, from the sensing, it is always the case that no matter which method you use, the target canvas geometry may not be accurate. There will be always some errors, approximate errors or sensing errors. So in our robot drawing case, the control has to somehow resolve this issue, even though there are uncertainties in the target geometry or even slight change in the motion. So we have to address all these problems to properly solve our drawing problem. So our drawing system consists of mainly these steps. So as an input, you can provide any kind of raster images. So these raster images can be AI generated, or even the artist can draw it. So given these images or typical raster images, we have to convert it to kind of vector form or spline form so that the robot can follow some kind of drawing motions to create the final drawing. So this is kind of a creation problem. Then this drawing path planner will create the drawing sequences. And then the robot actually then takes over this drawing motion to actually draw on the surface. So then which requires trajectory planner, which finds actually the joint configuration of robot to actually realize that motion. And then also we need to take care of the uncertainties in the environment from the controller. Furthermore, we need to also look into these steps. So after drawing path planner, create the vector form of drawing sequences. Again, as I said earlier, we need to estimate the canvas using vision or some other way. And then we have to represent the surface in some form. In our case, we use this quad tree for point samples. And then the point sample, the geometry actually should be mapped to the final 3D surface that would be mapping. And from this mapping, we find the corresponding pose of end effect locations. From that end effect locations, finally, we find the joint configuration of robot to finally realize. So we need all these steps, and we will go over this one by one, relatively quick manner from now on. So first part is the draw path generation. So in this case, as I said, the input can be the rest image. From rest image, we can convert it to vector sequence of robot path. But in our work, we considered three types of drawing path generations. And the first one is kind of obvious one. So if the user can provide drawing path, vector form from the beginning, then we can use it. And another possible option that we consider was so-called the TSP art. So given from the rest image, we find a kind of a long sequence of continuous line that correspond to original rest image. And then finally, kind of the obvious choice for converting from rest image to vector image is kind of stroke-based rendering. So you find the sequence of strokes that correspond to original rest image. So again, the obvious choice is using vector graphics engine. So there are many existing vector graphics. Also, there are a lot of recent vector, very nice research on converting from rest image to vector graphics. So we can use that one. Also, again, we can ask the artist to create this vector graphics to have drawing path in the first place. So you can use, like, for example, Adobe Illustrator, or in our case, we develop spline-based vector graphics engine by ourselves. So in some work, we use these engines directly instead of using rest images. But that is one obvious choice to create the vector path for drawing. And another possibilities that I said that I mentioned earlier was using a so-called TSP art. So this is some kind of art form where, given this original image in TSP art, we want to find kind of one single long continuous line which approximates the original image. This is so-called TSP art. And the way people typically generate this TSP art or TSP solution is that from the original input rest image, we kind of estimate the density of each point by stippling, so that this density related to stippling points is kind of approximate the tonality of original input. So first generate this stippling point, which approximates the density distribution from the original input. Then, using this stippling point, if you solve TSP problem for this stippling points at the sites, then you will have this kind of TSP solution. So this is one way to generate the kind of long continuous line of drawing sequences for robot. And these are some example of existing TSP art from the well-known artipiece. This is something done by others, not by ours. Now, in our case, our TSP pipeline is a little bit different because, first of all, we want to use the color drawing, not just simple gray or black and white line drawing. But the pipeline is a little bit different. Also, we have to make sure that the robot is efficiently capable of drawing this path. So we need some kind of path smoothing or path optimization to make it easier for robot to do it. So our pipeline, given this rest image, and then given the kind of color that the robot can use. In our case, we are using the pen art. So the kind of pen art, the kind of the pen colors that we can use is kind of limited, 4, 5. So then, using this limited number of colors, we have to optimize the color channels to approximate the color space original image. That is color processing. And then for each color channel, we have to independently create this stippling point. And then for each stippling point, we solve a TSP for individual channels. Then if you add up all these TSP routes, we get the final result. That is our TSP pipeline. A little bit more. So first of all, this color channel extraction or color channel separations, given the limited number of colors, there could be different approaches. One possible way is using this typical CMYK color space, which is often used in the 3D, which is often used in the color printer. So regardless of color input, we can just use the CMYK color input for color channels, and then we can add up to create the final color. That's one way. Or the other way around is that find the kind of the optimal color clustering, and then from that color clustering, we can find the representative color for each color. So they will correspond to robot to find out robot tools color. That might be two options. So we have tried both. And then the next step is for each separate color channels, we have to find the stippling points. In our case, we use this very well-known weighted Voronoi stippling technique to find stippling points to approximate the tonality of each channel. So this will be the stippling result for each color channel and the combinations. And then for each stippled color points, using each stippled point at the site for Voronoi diagram, sites for TSP, we solve a TSP problem for each channel using kind of, this is also very widely well known in this TSP, the optimal, the best well-known TSP solver, where we use a linear programming and a cutting plane algorithm. So we solve each stippling points for TSP path. And then if you combine it, you will get this kind of solutions. And compared to original image, a little bit is rough, but it's to some degree it's okay. Also, you can think of this as some kind of art form, even though they are not precisely exact. Now, the final step is that you can use this path for robot trajectory following process. But again, if you see the created path, it's quite jagged. Also have very sharp corners and many stippling points, which is not very good for robot ender effector to follow, because you need a high acceleration to stop and move and go the other direction. So we need some kind of path optimization. In other words, most physically, we need kind of bounded curvature path approximations. In our case, we use a simple the path decimation, but at certain path, it has really high curvature. We just cut it, make it smoother. So the left image is before optimization, and after right image is after path smoothing or path optimization. Now, that's the second way to generate the drawing path. And the final one is this very well-known, this non-photorealistic rendering technique known as a stroke-based rendering. So in stroke-based rendering, as you may know, so given this rest image, you want to find out the list of brush strokes that approximate the original images by minimizing their differences. So that's basically the idea of stroke-based rendering. But in our case, our focus is more like, instead of finding this bunch of random strokes, we want to find good ordering of these brush strokes so that it can mimic the way the human artists draw these images. In other words, we don't want some kind of random strokes, but we need to find the proper ordering of these strokes. So you may think that for this problem, some people can suggest kind of machine learning ideas to find or solve this issue. But the problem is that we don't have much database for this kind of artistic imagery or complicated drawing. There are some database for, like, for example, a quick draw data set for this ordering of drawing. But since we do not have such database available in our hand, we need to rely on some kind of rule-based techniques. So again, we want to find proper strokes that approximate the original input, but at the same time, we need to find the proper drawing sequences, not just random strokes. Here or draw there, draw here. Human never draw like that. But in our case, we want to have a robot kind of to mimic what human draw does, so that we can present this entire drawing process as some kind of art performance to the viewer. But that's kind of our difference from the existing stroke-based rendering. Then the pipeline of our stroke-based rendering is something like this. So given this rest image, first of all, we find the salient objects in the scene using the segmentations, phonetic segmentation more precisely. And then for each segment, we group a set of pixels, so-called superpixels, which is kind of a clustering of perceptually relevant pixels. And then we, at the same time, we also compute the depth map for each segmented, approximate the depth map for each segmented image. And then using this superpixel or clustering of pixels and a depth map to figure out this stroke ordering. So more precisely, for segmentation, we use a phonetic segmentation. So where we differentiate the kind of foreground and background, where foreground here is so-called things, where you can actually count the objects, and the background, what is called the stuff. It has some semantics, but it's kind of difficult to count, or rather abstract objects. We classify those two using phonetic segmentation. So things and stuff. And then we sort these things and stuff. In case of things, we use this weighted ordering of area of the image and the confidence of the segmentation results. We sort them. And also we sort the background based on some kind of symmetric ordering. So we will use this ordering as a drawing sequence. And then for each segmented pixels, we group the perceptually similar region, which we call the superpixel. People also call it superpixel. And then for each group, we find the centroid, which will be the beginning of strokes, painting strokes. They will serve as a beginning of strokes. Start from there and start to draw. And then, of course, we use we estimate the depth using existing depth map estimations for each segmented region, and then by combining those two, for each segmented region and for each subpixel from the back to front manner, we draw from back to front in that ordering. So if you see this, the final result of this is that you can see that the silhouette will be drawn first, and then more detail will be filled in. So here are some results. So this is the given input image. And then this is the stroke ordering. Now, then let me move to the next issues that we need to deal with. So the next issue is that once you have this stroke sequence or drawing sequence, now somehow you have to map this drawing sequence to 3D. And to map it, of course, we need a target canvas. So we need a 3D target canvas. We have to estimate this target canvas. And then you can map it. So to find out the target campus or estimate or reconstruct the target campus, we relied on two techniques. One is sensing by contact. So in this case, we use the manipulator, robotic manipulator attached with the force or torque sensor so that by touching the surface or target canvas, we can estimate, we can find the contact point from the force sensors. Then we can sample on the target surface. In this case, the target point will be mainly depend on this height. So it's some kind of, you can think of this geometry as some kind of height field. By touching on the surface, you can estimate this height field for each point. Then we store it, in this case, quad tree, or you can even store it KD tree. So you sample all these points. Then you can estimate at any random point by using simple bilinear interpolations, by finding the nearest neighbors. So this is kind of sampling by contact. This video illustrates what I just described. So by contacting different locations, we can find the sample points. Then you can estimate the rough geometry. Of course, depending on how many samples you will, as you have more samples, you will get more precise geometry. But that is one way. And the other obvious way is that you use a typical RGBD camera to sample the points of surface, then reconstruct that point of surface. That's another way. So we rely on two methods. Then you have some idea of your target canvas. Then you are ready to map from your 3D, 2D drawing sequences or drawing path to the 3D. But now, in this case, now you will encounter like a texture mapping problem in computer graphics. You have to map from 2D image to 3D or 2D drawing sequences to 3D. But then it's just like in computer graphics, you need to minimize this mapping artifact, especially this angle distortion. So we follow the typical computer graphics solution, which is conformal mapping. More precisely, we've been using the least squares conformal mapping to minimize angle distortions. And this is some result. So here, we want to try to draw these kind of patterns on this circular cylinder in the campus. So if you use the conformal mapping, you'll get this black pattern, which is very similar to the original input. But if you do not use the conformal mapping, you will get this orange, which is a slightly offset from the original input. Same here. The conformal mapping nicely preserved the original shapes, the final drawing. Now, up to this point, now we are almost ready to draw this pennant on the target surface, but still we have certain issues to realize that drawing on the target surface using the real robot. So this is a typical trajectory planning problem. So now we know this drawing path on 3D from the texture mapping or conformal mapping. And also typically we want to draw on the target surface perpendicular to the target, which means that we know the approaching direction. So to some degree, then you know the pose of end effector when you touch on the target surface, but still you need to find out the joint configuration to realize that end effector pose. But at the same time, since you need to follow the path, you need to kind of continuous joint configuration to follow the path. So in this sense, this is kind of IK problem, but since we need like a continuous joint configurations, we need to solve so-called the pathwise IK problem. In our case, we solve this pathwise IK problem to follow the anti-effector pose to realize drawing by minimizing the distance objective in the configuration space of joint. This is how we do it. And then next problem to realize drawing on the target canvas is that, again, the target canvas geometry estimation may not be accurate. So there could be always some errors in the convex geometry reconstruction. So from this inaccurate the convex geometry, and if you ask a robot to draw something on that inaccurate convex geometry, the robot may not be able to finish the drawing. So we need a better way to do it. And in our case, we use a very well-known technique in robotics control, which is impedance control. This impedance control, as far as I know, it is not very often used in the computer graphics, but impedance control, in this context, impedance control is the perfect case to use impedance control. So in brief, impedance control, we allow compliance or flexibility in certain direction, but we restrict the compliance in other direction. So in our case, we allow compliance on approaching directions, but we do not allow much of compliance on other directions. So by observing this idea, what we did was that since we do not know the exact canvas geometry, we slightly overestimate the target point set, which hopefully a little bit beneath the physical point set. And then by using this difference as an impedance, even though slight difference between this target and the physical point, since we have the compliance along this direction, we can still manage to draw a clean drawing on the surface. That's how we cope with uncertainties, the geometric constructions. And then the kind of the last problem that I want to address to apply to realize a robotic drawing to using the real robot is that how can you cover this large canvas? So since the robot manipulator has a limited workspace, which we call coverage, limited coverage, given some target canvas, when the robot is fixed at some fixed configurations, the kind of portion that the robot can reach is limited, which is highlighted as it is green. But since the robot can need to draw this or need to use the entire canvas, we need to find out the proper location of the mobile base so that the robot can reach here, 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 so that the robot can reach everywhere. Now, come to think of this problem, it is kind of obvious to formulate this as a kind of set cover problem. Here, the set will be the point set on the target geometry, and coverage will be defined by this coverage. So one may solve this problem in different ways. In our case, we try to simplify this entire problem. First of all, by projecting this 3D geometry onto 2D geometry, also approximate then that 2D geometry with a simple geometry like spheres. This yellow sphere, yellow circle, approximates upper drawing manipulator, and this black circle approximate the base mobile platform robot. Furthermore, we also kind of project this 3D geometry onto a 2D surface, 2D curve. So then we converted this 3D set cover or a coverage problem into a simple 2D problem. Then we try to solve the problem in this way. So this is a target kind of simplified 2D canvas. And then these circles represent the kind of coverage for the manipulator, the kind of simplified version. Then we need to find a kind of discrete set of these circles to cover this geometry. So to solve that, we first of all randomly sample these set of circles to possibly cover the entire geometry, and then in a kind of greedy fashion, we select some of those. So the way we approach is that we find a circle that contains as much as uncovered geometry, and then find another one that covers as much as uncovered geometry, and so on. So it kind of in a greedy way, and we can find all this. In this case, only 5 set of circles to possibly cover the entire canvas. And then from each circle, you can also figure out kind of a location of the mobile base. So we find all this mobile base. So these are the results. Then robot will follow these mobile bases. So this is one circular canvas, and the other more random canvas, another canvas. And this black circle represent the location of this manipulator. This black circle represents the location of this mobile platform. So once you found it, the robot platform moves from one pose to another pose to another pose. For each pose, it tries to a corresponding drawing. This is how we handle the large canvas. Now, let me then show some results. So this is our robotic setup. So we use 2 different kind of robotic setup. One is the 7-dub manipulator attached on the mobile platform. The other one is a dual robot arm. And we also have custom printing tools. And we also use a typical robotic softwares like ROS, Moveit, and Gazebo. And this is one example of drawing on arbitrary non-planar canvas on water tank or transparent sphere or bucket, water bucket, or the parking cone. Here, the input was just vector graphics. And this is drawing on a circular wall, which has a lot of bumps, small bumps, to quite accurately replicate the original input. These are some statistics for those results. And this is the result of TSP art. So the top is the input image, and the bottom is robotic replication of the input using the TSP art. And same thing for the input for Big Bang image and the straight light. The right is drawing by the robot. In this case, it's just flat surface. And some statistics. As you can see, the TSP solving and other steps is quite relatively shorter than actual drawing. And now this is a stroke-based robotic drawing. So here, what you can pay attention to is that not only we try to get the similar robotic drawing result like input, but we want to focus on how the drawing is actually executed. So people may have a different opinion, but we think that this is kind of similar what people will draw if they are asked, drawing sequence-wise. And these are some statistics as well. And this is a large scale drawing by using coverage planning. And also some statistics. I think I almost ended up my talk. So I kind of presented our recent robotic pen art drawing system that can generate artistic pen art on large non-planar surfaces using different types of inputs, and also kind of distortion-free mapping to nicely preserve the inputs on final drawing, and also use the impedance control to compensate for the uncertainties in the canvas. Also use coverage planning for large scale drawings. And even though this is kind of art type project, we actually think that this kind of system can be applied to non-artistic robotic application that requires continuous contact with the end effector and the target. So in our drawing project, we need to maintain the continuous contact with the pen, the target canvas. But if you replace this target with some other tools, you can use this technique to other types of robotic application, like milling, sanding, which is also important in industrial applications. There are other types of possibilities. So I want to thank my students who did most of work, and my colleague and my funding agencies. And then I want to conclude my talk, and I will kind of leave this video to show. This was kind of a little art exhibition that we did after we almost finished our robot drawing project, to kind of showcase the research problem to general public. I think I encouraged everybody to, I mean, if you work on some artwork, it is always to show your, not just research problem, the end result to the public, so that they can better appreciate what you do. So this is our way of doing it. So we thought that since we have this interesting robotic art system, why not sharing with others to show the possibility of this robotic art. Okay, so thank you very much. And if you have any questions, then I would love to answer. Thank you.
Thank you very much, Professor Yong. Yeah, it's a very nice talk, very nice presentation. Also, the final result, the art part is super nice. I really like it. So I see one question from the YouTube. I post in the chat so you can also see what it is. So the question is there any force control to keep the pen contact with the canvas, or control the width of the drawing? Can I ask one more? Like, is any torque or like a force sensor in the robot that you can actually read, so you can actually control the contact? Is that the approach?
Yeah, we didn't use force sensor or torque sensors to control the width of drawing. We didn't do it, even though we can. But the main reason we didn't do was because we are using pen. So the pen width is the final drawing pen width is always fixed. So no matter how you push it, I mean, if you push it really hard, the pen will be broken. So the pen width is almost hard to control. I mean, you may draw a really thin line if you slightly touch it, but that is hardly invisible. But if you push enough force, then it starts to draw some kind of fixed width. So this kind of, for pen drawing, controlling the width is almost not practical, I should say. But if you use other mediums, then definitely you can use this force control to control the width of pen strokes. for drawing strokes.
Yeah. Maybe I ask a question. I don't see any more. If you more, please the organizer pre-post it. I see it. Okay. I send you again. I found another one. So will there collision between the robot and the curved canvas? How to avoid collision? It's also from YouTube.
Collision between
sorry.
which and which?
I post it to you. The question is, will there be a collision between the robot and the curved canvas? So basically, the things you draw and the robot, will there any collision? How to avoid this collision?
I mean, collision detection. If any of you know me, I've worked on collision detection so many years, but I try to avoid this collision detection problem in this case because we wanted. I mean, as you saw already, the robot drawing itself takes quite a long time. So if you take into account collision detection, you will even incur more overhead. So one way try to avoid the collision detection problem, we kind of try to, instead of detecting collision, we kind of avoid collision. So by approaching always like from the perpendicular direction from the canvas, we can kind of maximize the possibility of avoiding collision. But again, of course, it does not guarantee the collision. Especially the collision detection, where the collision detection problem is more serious, is that I didn't show you much, but if you use two arms, there can be always collision between two. There can be always possibility of collision between two arms. So in that case, where you use multiple arms for drawing, collision detection problem is more serious. But at the same time, I guess you can use any type of existing collision detection library to detect and do things like that. But our main concern was drawing time. It's already too slow, so we don't want to add more performance degradation term by the process. So thanks for asking this collision detection problem. I'm very eager to answer that question.
I see from your website you're pretty expert in this.
Yeah.
Like you have a section of collision detection in your website. Yeah. So I have one more. My personal question is, I know in some artists, they not only drawing the picture. If you have a canvas, you have a vase like a water bottle, they're not only drawing outside the water bottle, but they also drawing inside the water bottle. Is that possible to use robot to do it?
That would be very, very difficult. I mean, even creating robotic mechanism itself, it'll be very, very challenging. I never thought about it. It'll be, I cannot imagine. How can you? I mean, if you can do it, you can solve a lot of other interesting problems. You put some like a cable type robot to some other like a tunnel. Types.
That's just my personal curiosity.
Thanks for asking that problem, though. Yeah.
Okay. If there's no more question, we should move to the next speaker. Is that okay?
Okay. Thank you very much.
Thanks again for Professor Yang's talk. Thank you very much.
Yep.
So let's move to the second talk. Oh, wait. So I think the second talk is Dr. Yi Zhang. The speaker is Dr. Yi Zhang from ETH. He's also my colleague from ETH. He is now a postdoc researcher in the Department of Computer Science at ETH. He researches at the intersection between architecture, computing, and robotics to make design and construction more connected. Yi Zhang got his PhD in the Building Technology program at MIT's Department of Architecture. Before MIT, he studied applied math and did research in computer graphics at the University of Science and Technology of China, where he researched his Bachelor of Science. And today's talk is about algorithmic planning for robotic assembly of building structures. So Yi Zhang, the floor is yours. Please go ahead.
All right. Can you hear me okay?
Yeah, maybe share a screen. I can check again.
Yep. Yep. Share screen. Can you see the slides okay?
Yeah, it's perfect.
All right. Yep. Thank you very much, Ziki, for your very warm introduction. It's always nice to be introduced by your friends and colleagues. And thank you very much for the invitation. I'm very thrilled to be here today to share my work with the AsiaGraphics community and to hear from you and to share this idea that I would like to promote, to use computation to bring architectural design and construction closer together. I have a bit of an unusual background, so I quickly go through my kind of personal story. I was trained in applied math back in my college days in University in Science and Technology of China. And then through researching computer graphics, especially in digital fabrication, I got very excited about the use of those mathematical tools to contribute to architecture, to the built environment. Then I moved to MIT and I did my PhD in the building technology program there in the Department of Architecture, where I learned about how design, like structural and architectural design, can be driven by structural performance principles. And for my research, I focus on performance in terms of construction, especially to make robotic fabrication more flexible to design inputs. And now I'm a postdoc fellow at the Computational Robotics Lab at ETH Zurich, where as a lab, our research unites under the theme of advancing robotic intelligence. And for my own research, I focus on building collaborative autonomy among multiple robot agents to boost construction efficiency. So in general, I kind of identify myself as a half computer scientist, half architecture engineer, and I've worked on algorithms to generate structurally efficient forms, design with reused building materials, and innovate new robotic fabrication processes and applying automated planning methods to program them to build structures more effectively. And a common theme that cut across all of these projects is that I would like to use computation as a medium to study the relationship between design, object, the builder, the agent who built the design, and the final outcome, the physical construction. And under this theme, one exciting topic is to study how we can advance robots' intelligence and ability to build things. In my vision of a future building industry, we can just give the drawing of a building design to a team of robots, and they will try to automatically plan and organize and execute collectively to achieve the construction goal. So in today's talk, I will start by briefly reviewing the history and state of the art of construction robotics, because I think this might be helpful for the AsiaGraphics community. And then I will share with you some of my recent work on applying automated planning technique to enable more capable construction robotics. And I will start by describing how an intelligent planning algorithm can help us automatically program robots to assemble arbitrary design input. And then I will show you how to expand this to model and program new robotic fabrication processes. And I will end with a resource planning method that can make the design more responsive to the upcycled material inventory. So let's get started. So how to use machines to boost productivity in construction is a topic that has almost 40 years of history. So at first, people aimed to replicate the success of automated manufacturing and trying to transport it into the construction domain. And the results was the invention of a variety of specialized construction machines like the polishing robots, bricklayering robot, etc. And in order to use those specialized machines, the design of a building is forced to conform to the ability of those machines. So however, this first wave soon died down both because of the collapse of an economic boom, but also because of the inherent rigidity of these building designs and the high expense of those specialized machines. So around 2005, together with the rising popularity of 3D printers and the decreasing price of industrial robots, a second wave of interest in construction robotics started. And however, unlike the last wave that's mostly driven by mechanical engineers, architects and designers start to become the driving force of this wave of development. To realize the potential of industrial robots as a universal machine. They believe that the design should drive the machine, and we should use robots to materialize more complex and diverse spatial forms instead of just a small set of standard forms. So in summary, research before the millennium focuses on using standardization to boost productivity, and the research afterwards, until now, aims at the flexible production of customized designs. However, despite the popular culture show us this is what construction robots should look like, which means, huge, gigantic humanoid robots working on site. There are a lot of technical problems to be solved before we can see something like this come true. And I think Professor Kim also illustrated this nicely. Like, we have three main type of algorithmic or technical problems we have to tackle for like construction robots. First is sensing, and then control and planning. And for construction robotics in particular, it can be classified into two types. One is on-site robots that can directly move around and work on the construction sites. And the other type is prefabrication robots, where the robot fabricate building components in a controlled factory environment. And then we ship these components to the site, and we use a crane or something like that to manually install them. So my work in recent years focused more on the long-term planning problems, and this has a direct application in prefabrication settings, but also I think it is a very important like a stepping stone towards more robust and capable on-site construction robots. There are mainly two research communities that are pushing planning-related research. The architecture robotics community focuses more on the outcome of the construction, and they push the frontiers of new material, new fabrication processes, and demonstrate the new possibility of design and build with this new technology. And on the other hand, the automated planning in robotics community, I think like some of the graphics community also contribute to this part, work on the more general purpose and effective planning algorithm that can work in many scenarios. From the architectural side, in the past 15 years, we've seen robots can be used to build large-scale complex geometries, and the fabrication process are very diverse, including like spatial assembly, welding, fiber winding, brick layering, etc. And if we classify the literature on construction robots in the past 12 years according to the fabrication processes, we can see that the top four are cutting, layer-based 3D printing. From my definition, I think drawing belongs to something like layer-based 3D printing, where you just have one layer, but have a very long, big one layer, and also stacking and milling. And in the sixth place is spatial assembly, where there's just 1/3 of the articles for cutting in the first place. So my interpretation of this is that the cutting process, we can transplant or trying to borrow a lot of our experience and algorithms, premature algorithms from toolpath planning for CNC machines. But the spatial assembly is something very new, something really enabled by those multi-axis or high degree of freedom robot manipulators. And there are a lot of unsolved technical challenges there. So I conclude that the technical difficulty of programming or planning for the robots is somewhat affecting the research progress of different fabrication processes. So compare with manual teaching programming method that's widely used in the manufacturing industry, programming of construction robots is much more difficult, in my opinion, because in construction or architecture, we have many different CAD models to be assembled, not just one that is repeated many times. And we do not really have an accurate physical reference at the first place to do the teaching anyway. So most current architectural robots use CAD software to do some kind of a semi-automated programming. So designers use visual programming platform like Grasshopper and Rhino 3D to program robots point by point based on digital models. But this process takes a lot of time, and the final generated programs are usually not really reliable. So using analogy of a 3D printer that like almost everyone is quite familiar with right now, the process of this programming process is like writing some scripts to generate the G code for each single unique geometry that you're trying to print ourselves by the designer themselves. And on the other hand, in the field of robotics, automated planning algorithms have been studied for many years, and it can be roughly divided into three categories. First, task planning considers symbolic level reasoning issues, like how do you chain together different discrete actions to achieve a goal. And trajectory planning considers how to find a collision-free trajectory that conforms to a kinematic constraints of the robot. And finally, putting these two together is task and motion planning, which is recently emerged a new field in recent years, allowing the symbolic and motion levels to be connected. For example, we can tell the robot at a high level, like make me a cup of coffee, and the task and motion planning engine will automatically reason like which action is reachable and which is not, and then chain together a task sequence as well as the motion plan to achieve this goal. So in the context of construction robots, those developments makes everyone in this field very excited because we see the possibility of automation of this programming process. But on the other hand, these existing work only provide a general algorithmic framework. Their performance on domain-specific problems still needs to be improved. So my work attempts to bring these two fields together. So I strive to simultaneously push for algorithmic development and architectural scale experiments to explore both the new geometric possibilities and more efficient algorithms. So today I will share with you some of my attempts in this direction. The first project investigates how to automatically program a robot to assemble arbitrary bar structures. So we want to generate the equivalent of a slicing algorithm that you would use in FDM printing to allow for more flexible robotic assembly of non-standard elements. But the planning problem here is much harder than just programming a gantry machine like a 3D printer. The spatial assembly requires us to think carefully about the assembly sequence. And for each element, we need to determine where the robot grasps the element and all the joint values of the robot at any single time of the entire process. All of these things together build up an enormous search space. And a valid assembly plan needs to satisfy the structural constraint that prevents us from choosing a very bad sequence like this one that build a cantilevering substructure without building any supporting element below it. This substructure will deform too much under gravity and causing harm to the assembly process. And the collision constraint that ensures the robot does not collide with itself, what it has built, and the environment at any time. As the robot builds more and more, the space gets more cluttered, and the sequence will influence the robot's reachable space. These constraints make these variables intertwine with each other and making finding a feasible plan even more complicated. While motion planning is a well-researched field, it only solves part of the problem. Like motion planner can automatically search for a collision-free trajectory in the robot joint space, connecting a given start and an end configuration. But the designers still need to guess the sequence and grasp and call the motion planner in a trial and error fashion to stitch things together. This obviously takes a lot of time and effort. And when the input design geometry changes, we need to reprogram all over again. So our goal is really to design an algorithm that can do this trial and error more effectively and systematically for us. So I think the best way to formulate this planning problem is using a framework of a state space search. The states represent as the gray blocks here, keep track of the current progress of the assembly. It includes a partially built structure and the robot trajectory for the current step. And an automated search process will go from the empty state where nothing is built and gradually adding elements one by one. And every time it arrives at the new state, it will perform a structural analysis to simulate the deflection of the structure and check if a robot trajectory exists for transporting the bar elements, as well as the collision of the robot trajectory. To check the collision constraint, 4 sampling routines need to be coupled together. So we first sample the grasp, and then sample an approaching trajectory on the bar itself. And then we use a constraint motion planner to check if it can find a collision-free motion to follow the gripper path. I think we're using exactly the same the iterative gradient, randomized gradient descent method as mentioned by Professor Yuan before. And finally, we use the motion planner to compute a collision-free path from the pickup position to this approaching configuration, like using standard planner like RRT star or bidirectional RRT. And the structural constraint requires a finite element analysis of the partially built structure. We use a first-order linear elasticity model, which involves solving a sparse linear system to obtain the structural deformation under self-weight. And we say this state is structurally feasible if the maximum nodal deformation is under a tolerance. It is very important to note that the search will automatically backtrack when the search is not feasible and consider other options until it reaches the goal. So we've already replaced the previously mentioned the tedious manual trial and error approach described before. But there are still challenges preventing the state space search from working for complex structures. We can think of a search of driving in a very thick fog without a map. And this means we can only rely on local information to make decisions without a global view. We need to decide where to go at each crossing, but there are just too many options to choose from. And each time we commit to a new action, checking a new state's feasibility has computational overhead because we need to call the planner, we need to do the finite element analysis. And finally, we want to avoid hitting dead ends too frequently and backtracking too much, which might make our search run for eternity or a very, very long time. The first observation we make in this work is that the standard forward search that just described can easily get stuck because of the collision constraint. And here's the example that the search has too many seemingly innocent options at the beginning, and it keeps making those greedy decisions and only realize, okay, at the very end, an element cannot be reached, and we need to backtrack many, many steps. And to fix this, one key algorithmic insight is that backward search can dramatically reduce those collision-related dead ends. Searching backward is essentially the idea of assembly by disassembly, where we move elements from the complete state to the empty state, just like in a Jenga game. Because we go backward, the planner cannot choose elements that are inside the shape at the beginning because they are pruned by the collision checker. And in doing so, much less backtracking is needed in the long term. In addition to a search direction, a good heuristic is very important to guide our search to save more unnecessary explorations. It's like the road sign that tells you which direction is more promising to get you closer to your goal. Well, an obvious heuristic is to rank the element by the height and always prioritize removing the one that's higher up. This strategy works for many shapes, but failed for a shape like this tower. It would bias the search to remove all the tension ties at the top, and the entire tower will deform as a result. Thus, the search will get stuck in a dead end. And to fix this, we introduce a new heuristic that's bootstrapped by a structurally feasible sequence, which would guide the search to adhere to this example sequence while still allowing flexibility to balance the collision constraint. To obtain the sequence, we first run a forward search without considering the robot, just the structural constraint. And we observe that this heuristic offers a really robust and generic solution to guide the search effectively. Now, combining these two strategies can really give us a fast and scalable planning algorithm. So in contrast to a naive forward search algorithm that cannot terminate in hours, our approach can find a feasible plan for this fairly complex bar structure in 3 minutes and outputs a detailed sequence and trajectory that can be directly loaded on the robot. And we can also plot the maximum nodal deformation along the assembly steps, where each dot on this plot represents a partial structure simulated with the FEA along the sequence, and the y-axis is the maximum nodal deformation of that step. And we can see that the deformation is really controlled below the prescribed tolerance, indicated by the yellow line. And I believe the true power of having this computational planning system is that we can now plan to build all these different shapes without changing any lines of code. And it takes less than 6 minutes of computation for any of these, like a variety of shapes. And another cool thing or advantage of our planning formalism here is that it can be easily extended to other types of robotic fabrication process with a similar pattern of actions. Here we show a spatial extrusion process, which is kind of similar to drawing, but you can imagine like the robot is holding a pen that's drawing in the air, and wherever it traverses, there's a beam or a line of plastic that kind of just solidified right after it traverses. We can now plan for extruding all kinds of complicated topologies and geometry, like this topology optimized beam that achieves efficient load transfer. And you can see this, the last one takes only like under 4 hours to print. And here's another example of a famous and classic topological shape of the Klein bottle. And this planning framework allows us to really experiment with different motion planners. And these motion planners offered by the robotics community really start to become a commodity tools that we can really plug in and play and see which one works the best to achieve our design outcome. And what we gain here is not only expansion of geometric possibilities, but it also means flexibility in working with different machines. It doesn't matter what robot brand is, how many joints they have, and what customized manufacturer you're using. The planning algorithm is generic and allows plug and play for robot models. And here's one example of using our approach on an ABB robot on a large linear track, a simulated example to extrude a large-scale topological optimized beam that span across 3 meters. So to summarize this part of the work, we designed a search algorithm to automate the planning of robotic assembly. We've shown this framework makes assembly flexible to various design inputs and can be extended to plan for spatial extrusion. Although the current implementation still takes minutes to compute a plan, it can already act like a design check. Ultimately, our goal is really to use this planning framework to make it fast enough to serve as an input in the design process. So by automating robotic assembly, we not only enhance our capability to construct previously impossible shapes, but also gain insights into constructability. And now that we have given a solid planning method for robotic assembly, we want to expand this success to support innovation of other new robotic fabrication processes. Well, robot does not, in those new fabrication processes, the robot does not only just do pick and place of beams, but also change tools, it cuts, it drills, and so on. So as researchers in this field, we all spend a lot of time thinking about how to coordinate those actions and program the motions. But the resulting prototype program usually cannot adapt to new input well enough, and there's a lot of wasted, duplicated programming efforts. And this is really a painful experience that many of us share. And this project really tried to build a generic computational workflow so that designers can model their process on a high level, and the detailed robot plan can automatically be computed. And we take inspirations from computer programming. When you work with a programming language like Python, the composing of executing a program roughly has these three phases. The first, you write code that consists of instructions and algorithms that describe the desired behavior of a program. And the compiler takes over and turns it into a low-level representation the machine can understand and execute. And finally, the processor dispatches those instructions to basic computing units, which are specialized to do operations like adding and multiplying numbers. So in our context, our basic computing units are inverse kinematic solver and motion planners. And our goal is to build this compiler for describing the construction tasks and translate them to a format that the motion planner can operate on. And to ground up discussions a little bit more, let me introduce you to a case study from my colleague Victor Liang at the Grandmaster Encoder Research Group at ETH Zurich. And his research proposes a new process where the robot can assemble spatial timber structure with those tightly fit integral joints. Well, humans usually use a big hammer approach to assemble those tightly fit joints. This obviously does not work well with most of our industrial robots today. If you really do that, you push really hard to get the robot to use a hammer, the robot controller, the warranty, and your lab technician probably will scream at you at the same time. So Victor had this idea of designing those remotely controlled clamps that can be mounted on the timber and can generate a large amount of pulling force. Then the robot arm can simultaneously push the timber elements into the joint together with the clamps. So this will overcome this the large amount of friction force required by those integral timber joints. And with this concept, we can already start to organize robot actions and visualize the process here. So the challenge we face here is that there's just so many tasks to be handled and even more motions to be programmed. Even for the seemingly innocent 14-element structure, it would require 671 tasks. And manually organizing these things is certainly not a good idea. So to overcome these challenges, we introduced a flowchart-based compiler and a motion solver. So the compiler allows designers to express their process in this compact, intuitive format. So it's kind of I think it's very conceptually, it's very similar to a finite state machine. So for example, our timber assembly processes flowchart is here. And an important feature here is this conditional statement here. They will automatically curate a variable number of clamp manipulation depending on the considered beam. So starting from the flowchart, the rest of it is automated by our algorithms. So the compiler first translates the flowchart into a long sequence of robot motions. And what is the key here is the compiler breaks down the tasks into smaller movement chunks that correspond to the motion planner's capabilities. For example, placing one single beam takes 69 robot motions, and the color of those little blocks here correspond to their type of motion. Then the motion solver takes this long list of movements and automatically computes robot trajectory for each one of them. And the trick here is to smartly group the motions together. And for each group, it identifies the most constrained motion and propagate outwards. So without getting into too much details here, I just showed that the results shows this strategy greatly reduced the planning time compared to a naive solution that sequentially solves motions one by one. So now it's time to see the fruits coming out of our compiler solver. So this timber structure has 40 elements and involves 2,400 robot motions altogether. And planning the entire construction process takes about 5 hours of computing time. And as you can see, many of the motions involve operating in a tightly cluttered situation, and our solver is crucial for finding those intricate trajectories. And a big advantage of this workflow is, again, this flexibility in adapting to new design geometry. Here I show another design planned and executed using our approach. So in the paper, we also show examples of using this approach to model other previously proposed robot processes, including a multi-robot assembly and a robotic winding process. And what we want to emphasize here is this flexibility in modeling different robot processes, and this can act like a bridge to utilize the power of computational tools already exist from the robotics community. So in summary, we provide a compiler solver approach to fill in this important missing gap between designing a new robotic fabrication process and the automated planning of robot motions. And we've shown its effectiveness in planning for a new timber assembly process, and it provides designer with a flexible means to test and deploy new robotic fabrication possibilities. So finally, I want to talk about a different type of planning to switch from planning actions of robot builders to planning how material resources are used. The main motivation here is to limit the usage of new virgin materials in the built environment and think about how to upcycle or reuse materials that are already available for us in structural waste, either from existing buildings or from the natural world. Things like tree branches that are normally chipped, degraded, and turned into carbon emissions within a year, we could instead try to salvage and use them in generative design process to construct structures with high strengths, where the strengths really come from that amazing internal fiber structures of trees. However, compared to designing in an unconstrained manner, where an infinite material supply, with an infinite material supply, reusing existing material requires designers time, effort, and creativity to devise structural forms with a constrained kit of parts. There's an increasing interest in the idea of designing with reused parts, but we are nevertheless missing a generic computational assignment workflow that can cater irregular inventory geometries and can find an optimal assignment while staying responsive to design change. So this work addresses this need by proposing a matching algorithm that finds the optimal assignments between the target design and material inventory. And the important ingredients here are first using a geometric registration algorithm, classic 1 ICP, to compute pairwise shape differences between the design set and the material inventory. It then use a specialized matching algorithm, like a Hungarian algorithm, to find the optimal matching, since here we can model this as a linear assignment problem. And with this algorithm, we can start to optimize a parameterized grid shell, not just to maximize the structural efficiency or structural stiffness, but to maximize the use of inventory of tree branches that we have available. You can see here, as we are changing the designs, the matching are changing, and the matching score is also changing. And again, combined with the advances in robotic fabrication, the complexity of building this can be minimized. Here we use a robot arm to machine the tree. Because we cannot leave the barns, the outer layers of the tree on because of the fireproof requirements. And the assembly process itself cannot be simplified. We're still working with a kit of parts, but our kit of parts is quite unique. It is driven by the natural geometry that we've encountered from the found materials. And this idea can be extended to different types of geometry. For example, reusing timber elements from a disassembled house to design greenhouse domes. And our optimal matching algorithm can give us the best way to assign and cut these salvage materials. And with our tool, designers can start to have a live feedback on material utilization and other objectives while exploring different design options. And it helps them to quantify the trade-off between sampling a design data set with a multi-objective optimization and start to identify this Pareto front between the total floor area and the matching score. So we have also used this technique in our teaching at MIT. Students, architectural design students, use this matching tool to give traditionally undervalued waste materials a new life. For example, start to build a spanning structure with oyster shell pieces, making a light cover with broken beer bottles, and using abolished shared bike frames to start to build trusses. So in summary, in this work, we've shown how a resource assignment algorithm enables us to design with upcycled material resources. And this can start to open up a lot of room for creativity and the use of computation in new ways. So to conclude, today I've really quickly show a few design and construction problems and how the planning of these things can be assisted by computation, by algorithms. And in all of this work, existing computational tools can only solve part of the problem, and we need to invent new tools and a more integrated framework to have them all work together effectively. So just to recap, in the first project, we use an integrated search algorithm to plan for both assembly sequence and robot motions together to program robots to assemble arbitrary design input. And in the second project, we consider a compiler-solver approach to help program new robotic processes. And in the third project, we demonstrated an optimal assignment algorithm that enables us to design with upcycled material resources. And I think this is really a small sample of what automated planning can do. And although we mostly focus on robots, future work would include a more integrated framework that considers human, robots, materials all together, and an idea of a reactive planning to automatically come up with long, short adjustments when construction reality really deviates from the initial plan simulation, and also bring this work really out of the lab to push for applications in real projects. And finally, before I really wrap up, I would also mention that none of those work will be possible without great people. So a huge thank you to all of my mentors, collaborators, lab mates, and so on. But of course, the funding agencies that make this possible. So thank you very much for listening. I would like to open it up for questions now.
Thank you, Yijiang, for your very nice talk. Is there any question posted on the internet? Yeah, because Yijiang is my colleague, so we have discussed many of the questions personally a lot. So if there's a question, I prefer to on the internet, I prefer to ask first. No? Okay, no, okay, no question. So maybe let's not instead of ask question, let's discuss like what do you think of the future of the robotic constructions? How should we, or how this field should grow? What's your vision? It's using robots to build it. It's the ultimate way, or is like what this field could go?
Yeah, that's a very, very hard and challenging questions. So I think, I think I first got into this field because of just personal interest and this using robots, programming them to build things is cool and exciting. But later, as I get deeper and deeper into my PhD, I start trying to find motivation in a bigger picture. I think most of the construction robotics nowadays, it's not, as I showed in the history, it's not not just to boost productivity, but also it's just really trying to use robots to solve the labor shortage problem. I know labor shortage might not be a problem in the Asian countries, but as the world is moving into with more, the educated population is increasing, I think the labor shortage will come in some day and trying to use robots to at least assist repetitive and tedious tasks in construction. Those tasks that cause injuries and use a lot of time, cause people back pains or something like that, or dangerous. I think this is definitely like a much needed research agenda. In terms of where this is going, I think I've also shown like there's two types of construction robotics. One is offsite and one is onsite. I think like most of the research nowadays is still focusing on the prefabrication setting. Like it's basically where we're still like trying to grow out of the manufacturing setting, like controlled factory. How do we program robots? It's precision engineering. But I think in the future is really trying to push to the onsite. Trying to encounter for the how do we sense? How do we make the vision system working? How do we make multiple agents to collaborate? I think is very important and very hard. So I think we're just starting, and this is very exciting research area.
Yeah, I agree too. So thank you again, John, for your very nice talk. And I think this comes to the end of this webinar. If without any more question, we will conclude. It's organizer, okay? Okay, yeah. So thank you everyone to coming for this webinar, and I think see you next time. Thank you.
Thank you.
Bye-bye.
Thank you, Ziki, and thank you for the organizer. Bye.